we will want its IYY and its IXX. And I'll use the given coordinate system here where x is at the origin's at the center bottom of my shape. And I need my dimensions, so that's 0.5 inches wide, 0.5, and 0.5 inches, and 6.5. So first thing, just like we saw with the centroid problems, I need to, because this channel shape is not a simple rectangle or simple triangle, I want to break this up into easier to calculate subshapes. So just simple rectangles or simple triangles. So I can take this outer rectangle piece as one of my shapes, and then I can cut out this inner shape the same way we did for centroids. In this case, I can then do it in 2 shapes rather than 3 shapes. So by kind of my rule of thumb, the fewer shapes, the better. And then for fewer shapes, if you can have more positive than negative shapes, that's better. So I would say I would rather do 2 shapes, even if one is negative, than 3 positive shapes. It's just less work. So this is how I'm going to present it, but it's not wrong to break it up into 3 shapes or more shapes if you wanted to only deal with positive shapes. The first step is going to be solving the centroid problem for these 2 shapes. So for each shape, I need its area, its x-bar, its x tilde, y tilde, ax tilde, ay tilde. And then that we'll use to get our x-bar, y-bar. This is how I've decided to split up into shape 1, shape 2. What's the area of shape number 1? 91 square inches. And for shape number 2? Right, it's negative 78 because I'm cutting it out, and cutout shapes will have a negative area. And that'll be important because when I then find the total area, it'll be 91 minus 78. So 13 square inches is the amount of positive area of my shape. If I go to x tilde, what will x tilde be of shape number 1? So how far is the centroid, the vertical centroid of my shape from the y-axis? So for shape number 1, because of where the origin was placed, since it's placed at the center, I'm going to find that my x tilde for shape 1 is 0, and for shape number 2, it's going to also be 0 because they're both centered on the y-axis. Had I placed the origin at the extreme left bottom, then these would have been non-zero here. So these are always with respect to the origin of my system. For shape number 1, what will my y tilde be? 3.25. It should get 3.25. It's going to be half of its height, because this is how far from the x-axis is the centroid located. So shape 1, which has a height of 6.5, half of that will be 3.25. And its base is on the y-axis. And for shape number 2, what is my y tilde value? Right, just 3, half of its height, and also the bottom of its is also shared with the x-axis. So I get 3 there. Everything I need for these steps is already on the table. A times x tilde is just going to be 0 and 0 and 0. And my a times y tilde, I have 91 times 3.25 is 296. Negative 78 times 3, negative 234. If I add those together, I get a positive 62. So to find my centroid, I'll get 0 over 13, which is 0, and 62 over 13, which is 4.75. So if I draw the centroid here, this is my x tilde, and it measures 4.75 from the x-axis. And my y is also my y prime axis. Right, so this line, this line, this line, this represents the centroid of my figure. Questions on finding these values. Again, these are relative to where the original origin of my system was. when I find my moments of inertia, those are actually not going to, it doesn't matter where the origin of the system is, all that matters is the orientation of that coordinate system. I'll get the same moments of inertia either way. So in the next section, I add on to this table. For each shape, I want its IXX prime, its IYY prime, the DX value, the DY value, ADX squared, and the ADY squared. Now I'll use that information to find what I really want in the end, IXX and IYY. For shape 1, we want to find the moment of inertia of shape number 1 about its own centroid, and that's the IXX prime. So again, we look at shape number 1, it's 6.5 inches tall, and it is 14 inches wide. So for shape number 1, we want to find IXX prime, so about its own centroidal, horizontal centroidal axis, what is the area moment of inertia? So for that, we're going to take its dimension that's perpendicular to that and cube it. So perpendicular to the horizontal is going to be the 6.5 cubed times the dimension that's parallel, that's the 14 inches, and we divide that by 12. So what do you get for IXX prime of shape number 1?
320.4.
Right, I'll just write 320. So yeah, it's about the horizontal axis is our IXX, so that's why I'm cubing the vertical dimension and then leaving the horizontal dimension to the first power. If we look at, well, let's do the same thing for shape number 2, the cutout shape. Again, talking about the horizontal axis. This shape, though, is 6 inches tall and 13 inches wide. So what should the IXX prime be of my shape number 2? Yeah. Right, it's a cutout shape. Cutout shapes have negative areas, and they are going to get negative moments of inertia. So a negative 234, if I add those together, I get 86 for that summation. Right, so that's their individual resistances to bending around the horizontal axis that passes through their centroid. I also want for each one their resistances to bending around the vertical axis that passes through their centroid. So for shape number 1, it still has that those same dimensions, but now around that y-axis that passes through its centroid, the perpendicular dimension is now the 14, and the parallel dimension is the 6.5. So the same numbers, but the larger number gets cubed rather than the smaller number. So for shape 1, what's my IYY prime? And again, that's coming from 14 cubed times 6.5 divided by 12. So again, larger number that way. And for shape 2, same dimensions as before, but now I'm going to be cubing the 13 inches and then multiplying that by 6 inches to the first power. Divide that by 12, I get negative 1099 for shape number 2. Again, negative because I'm cutting it out. So 388 I get as my total. I now have to make that adjustment because the centroids of my individual subshapes are not the same necessarily as the centroid of the composite shape. I said the centroid of the composite shape was up here, but for example, through shape number 1, the horizontal centroid is down here. So this distance is going to be what I call dx, at least for shape number 1, so dx1. So I have to make that adjustment term when the axes are parallel, but they're not on top of each other. They're offset by some value. The dx term, I defined dx, remember, as y tilde minus y bar, and dy was defined as x tilde minus x bar. So this is a little bit counterintuitive. Dx is defined by the y terms. Dy is defined by the x terms. Again, I'm finding these distances that I have to offset the pair of axes. But all the information is already on the table. So for my dx value for shape number 1, I am going to take its y tilde minus the y bar. So for shape number 1, I get a dx value of negative 1.5. Again, it's 3.25 minus 4.75. And for this, I don't care if you put negative or positive here. It's not going to matter because in the only thing we do with it is square it anyway. So if you put 1.5 or negative 1.5, that's fine. Either is fine for me. And for shape 2, I want to take its y tilde of 3 minus my y bar of 4.75. And I'll get a negative 1.75 for that dx. And then I have to find that horizontal offset. I have to find the dy values, which will be x tilde minus x bar. I have 0 minus 0 is 0, and 0 minus 0 is 0 again. So really, I didn't have to make any adjustment because as far as the vertical axes are concerned, they are all the same. The composite shape, and shape 1 and shape 2, that y-axis is the same for all of them. Again, I have all the information I need already on the table. I just have to take my areas times dx squared. So I'll get positive 205 for shape number 1. For shape 2, I have a negative area times a dx squared. I'll get a negative 239. And that gives me a negative 34. And finally, for a dy, I have 0 and 0 because my dy terms are both 0. So the last step is I can put it all together to find my area moment of inertia of the composite shape around the x prime and the y prime axes. So for IXX, I'm going to take that 86 plus all of my ADX squared terms. That'll be a negative 34. So I'll find my total IXX to 3 decimal places. I have 52.3 inches to the 4th power. Here I did rounding. Here I rounded a little bit less. And for IYY, I take the total IYY prime of 388. I add to that my total of ADY, which was 0. So I'll find 388 inches to the 4th to be my total area moment of inertia around the y prime axis.